the setup would be the same as the one in Davesh's talk, where we consider C to be a family of a flat family of proper integral and integral curves with locally planar singularities. For example, you can think of this as these are the spectral curves on the Qizheng systems, and then we consider that compatible by Jacobian fibration associated with this family of curves would be I would call this from J to B, which I would call this map to be F. So in the talk, I will first start with this general setup where I will talk about general compatible Jacobian fibrations associated with a family of curves. And at the end, if time permits, I would come back to Lagrangian fibrations and discuss what's special about it. Okay, so so then this is the same as the setup in Davesh's talk, and at the end of his talk, he mentioned that so there is a universal family which induced the derived equivalence of this one, which I will recall what this E is due to everything. So I'll tell you what this E is like, but before doing so, let me set up a notation. So starting from this E, we can induce a cohomological correspondence because we can take characteristic classes of this E, which gives a cohomological correspondence, which is our Fourier transform operator. So intuitively, this F can be think of this. We take the Chen class and this universal sheaf, the Poincare sheaf. However, the reason I put the quotation marks because this is as mentioned by Davesh already. This is not a perfect complex, and this is a singular variety. So in order to define the Chen character, you have to go through. You have to use the tau class used by Baum-Fulton Macpherson in singular Riemann-Roch. But still, in order to make life easier, let me just write this way. Okay, so then let me first state the May theorem. So the May theorem, there are three parts. The first part is the motivic decomposition conjecture, which says that the statement is that the Gabber's decomposition theorem for the morphism given by compatible Jacobian fibrations. So the decomposition theorem is induced by its motivic. By motivic, I mean it's induced by algebraic cycles. So if you think about the statement over a point, so for a smooth variety which is over a point, then this is exactly the Chao-Kuhn of the existence. The conjecture, sorry, the statement says that it is so it has a Chao-Kuhnist decomposition, but this is a relative version of it where you involve singular fibers.
So in that sense, you consider only the decomposition on cohomology or on Chao? So the more precise version of this is stated using relative Chao motives over n. But yes, but yeah. But the easy way. I thought that there was a paper by Aranturo saying that
cycles appearing in the decomposition theorem where algebraic means the operators, the projectors appearing in the decomposition theorem were algebraic. I thought there was a result by Arapura. Am I wrong?
Was it for the perverse or just Leray?
For what more reasons?
The operators giving the decomposition theorem. So the decomposition theorem decomposes the cohomology, so there are projectors and
yes, homological projectors. It's so this part says that the decomposition theorem. So the way I write it. So this decomposition, maybe let me just write it. Is induced by algebraic cycles. So yes, so what we really do.
Generalization of the fact that for an abelian variety the Q-net projectors are algebraic.
Yes. Yeah. This is in that if you delete all the singular fibers just by focusing on the smooth part, this is a Denisgner-Murre's theorem exactly. So, but just one remark concerning this statement. So, in many of the statements about the study of abelian fibrations or integrable systems, usually the strategy is that we understand the generic fibers, which are abelian varieties, and so we can prove things there. And then once we obtain these cycles, then we just take the closures of these cycles. But this is much more subtle than that. So the issue is that once you have so over the smooth locus you have the projectors, but after taking closures, they are not necessarily projectors, and they almost never are projectors. So in particular, you have to really understand what are those algebraic cycles over the singular locus, which I will explain. And it's not hard to imagine that they would be coming from this F. Okay, so this is the first part, which says that the decomposition theorem, in this case, is motivic as conjectured by, this is the general conjecture by Corti-Hanamura, which is called the motivic decomposition conjecture. But certainly in general, this is wide open because even, as I said, even just for a smooth projective variety over a point, then this is the existence of Chong-Kunis decomposition, which is more or less one of the standard conjectures. Okay, so this is the first statement. The second statement concerns the multiplicativity. Which is that the perverse filtration. So since I'm describing an increasing filtration, so I will use a slightly different notation as Davesh's. So I will put a dot here. So we'll hold this one. Then, so the perverse filtration is multiplicative with respect to the cut product. And this corresponds to the first part of Davesh's proof, Davesh's the theorem, and then the last part is how you handle term classes. So the version I'm writing here is that if you consider Fk, which can be thought of the degree k part of the universal family, and you apply this to any class on JC bar, and this will lie in the case piece of the perverse filtration. So in particular, two remarks. So the first is that.
Excuse me, yeah, sorry. Did you say something about the smoothness of J bar, or are you assuming?
Yes, yes, the same setup as in the vicious model. Yes, thanks. Sorry. So the two remarks. The first is that I state the theorem as this for convenience, but really for the second part and the third part. So we prove everything in for relative motives over B. So both 2 and 3 they actually hold. There's a motivic version and also sheaf theoretic version, depending on what kind of setup you want to. So this is the first remark. And the second remark is, so like in Davesh's talk, so one of the key method for studying the cohomology classes for Qizheng systems and other settings which are like abelian fibrations. So one of the key tool is the tautological generation. Like in the Qizheng setup, this is the theorem of Markman, which says that every cohomology class is tautological. But this is really, and then after having the tautological generation, then you can, like, for example, you can try to understand the perverse filtration using some other filtration, for example, the Chen filtration. But this, in general, is wrong. So even for a single planar curve, and you consider its compatible Jacobian, then usually there are more classes than the tautological classes you can write down. But the third part of the theorem tells you that, so in some sense, one can generalize the tautological classes by, so instead of using classes from the S, the surface S in the vicious talk, we can do, for example, using classes on C, like Claire mentioned. But even more, we can just feed in any classes on JC bar. So we think of this F as a correspondence from JC bar to itself. So in this sense, every class is tautological. So using this generalized, so every class is of the form. And you take the k-squared these and you. So this is because F is so this is because for any things, for any class, you can write this as F inverse. So therefore, any class any class can be expressed in terms of it can be generated by expanded by classes of this form. So in particular, using 3, we are able to understand the perverse filtration by Chen filtration if we enlarge the set of tautological classes. So in particular, it's not hard to imagine by basic intersection theory that the 3 will tell you, the third part will imply the second part of Davesh's talk. Because this is the most general class you can take. Okay, so this is the main theorem, the real main theorem, the real main theorem I would explain. Any questions so far?
Sorry, is the Fk related to the F? Like?
That's the degree K part.
Okay.
So F is an isomorphism.
F is an isomorphism which comes from the fact that this is a derived equivalence. So yeah. So really this K is the Chen grading. So if you think of F as the total Chen character of some sheaf, then Fk is taking the K's Chen class. Okay, so I'll explain the theorem first over a more simplified setting, namely.
Sorry, so could you say again where do you need a curve? That is important to find Jacobian of a family of curve. Why isn't it working for any abelian scheme or practical abelian scheme or D?
Yeah, so in the paper we wrote in the way that if there is if you can extend the Poincare line bundle from the smooth locus to the, so if there is a E, then you would have, all the other things would work. But the issue is to have this derived equivalence, which is constructed by R ranking only for the compatible Jacobian. That's the most essential, and essentially the only place we would only work. I only state things for the compatible Jacobian fibration. So yeah. For example, if you consider a Lagrangian fibration with integral fibers, then if one's able to extend, for example, the work of Fedorov and Arinkin to something like this, then all the other things would work identically. So also, there's one thing I want to mention is that the existence of a derived equivalence from abelian fibration, particularly in the setup of integrable systems or Qizheng systems, to some extent, this was predicted by the geometric Lagrange correspondence, but to the best of my knowledge, so far, for other groups, we do not have such a construction of this E. So that's the reason that, so the E is really so starting from E, then we have this Fourier transform operator, and then we have all this theorem. And I hope it's clear that this Fk will govern the tautological classes as stated in Davesh's talk. Any other questions concerning the theorem? Okay, so I will explain quickly the theorem. So if you assume all the curves are smooth, then this is just a Jacobian fibration, which is an abelian fibration, and all these three parts are not new. So I'll first explain the story there. And then after that, I'll explain what's the essential difficulty of generalizing these stories to the case of with singular fibers, and what we have to do. So in this part, the setup, we consider F to be an abelian B scheme of relative dimension G. So then, this part essentially is due to Beauville, and also in the relative setting due to and that idea is that, so even we study, if we are interested in the questions concerning one abelian scheme, we should consider its dual. So the idea is that we want to use the geometry of dual fibration to produce produce interesting algebraic cycles. So I will divide this process into 3 steps. Yeah, when I was a first graduate student, I really spent a lot of time learning how to use this kind of eraser. Okay, so let's see how the dual fibration can help us. So the first part, of course, is Mukai's coherent duality, which says that there is a so let me just say it directly. So there is a Poincare line bundle which induce equivalence between the derived category of coherent sheaves on A and A dual. So I'll write this to be the Fourier-Mukai, and this to be the Fourier-Mukai inverse. Since I will concern the cut product So I also have to keep track of some structures on both sides. For example, so the tensor product on this side will be exchanged with convolution product defined using the group structure. Okay, so then, then once you have some algebraic, once you have some sheaf over the relative product, then we can descend everything to cohomology, so the correspondences. Again, for notational convenience, I will state everything in cohomology, but I hope it's clear that everything's algebraic. So then I will have the Fourier transform operator, which I call F. And an F inverse. What we do is just descend everything from coherent sheaves to cohomology. And in particular, so that this exchange of structures will become that so this Fourier transform exchanges the cut product here with, again, the cohomological convolution product. So a quick remark is that here the convolution product, which is, you have two classes on a dual. You pull them back on the relative product and use the multiplication map to push it forward. So in particular, this convolution is of pure degree. So if you start with a class in HD, another class in HD prime, you will go to a class D plus D prime minus twice the relative dimension. So it's a pure degree operator, which is important. I'll see what happens in the singular case. Okay, so these are just so far we are writing down the things we are familiar with. We haven't done anything non-trivial essentially, but then well, as long as you have a derived equivalence, then we can have a decomposition of the relative diagonal. So more precisely, by the derived equivalence, then since we know that you take the Fourier transform and a Fourier Mukai transform and compose it with Fm, you get identity. So to set everything to cohomology, we know that the relative diagonal. So we have a decomposition of the relative diagonal in terms of this F. So it's for the degree reasons, and you will have Fi inverse composed with Fj. So I'm thinking about this notation to be the composition of correspondences. Okay, so far we have a decomposition of the relative diagonal. Then, but still, if we just have things like that, it's not that useful. We cannot use this to produce a motivic decomposition. So the reason is that these, I'll write this as Qj. So we want, so in order for this decomposition to be useful, we want these cycles to be orthogonal projectors. This QK form orthogonal projectors. By this I mean if you compose with itself, you don't do anything, and but if you compose this with something else, you get 0. And once you have this, then really the decomposition of the relative diagonal will give you a motivic decomposition of the cohomology. And of course we have it. And the desired statement is given by a tautological relation. I'll write down what the tautological relation looks like. And this is the new places which is not read off directly from the derived category, from this like formal consideration. Okay, so this is implied by the desired statement is implied by the following tautological relation, which I will call strong Fourier vanishing. And it's not hard to guess there would be Fourier vanishing without strong later. So I'll call this as FV, which is that if you have Fi, and you compose, Fi is a correspondence from A to A dual, and you compose it with Fj inverse, which goes from A dual to A. And this is just 0 if I plus j is of the wrong dimension, which is 2g. So, and then it's not hard to check once you have, oh, it's not equal to 2g. Once you have this, these relations on, these are the cycle relations on A cross A over B, then you get that this DQK form the projectors. So in particular, you get a decomposition of the cohomology, which will be known as the Beauville decomposition, cohomological Beauville decomposition. So, which says that the entire cohomology of A decomposed into well, so to make the consistent notation with this, I should write J. So the J's part is contributed by Fj, F 2G minus J inverse. Okay, so this is how you get a decomposition. And then in this particular case, in the abelian scheme case, this is actually a splitting of the perverse, or more precisely, Leray filtration of the morphism from A to B. So yeah, consequences. So actually, having this Fourier vanishing, the strong Fourier vanishing, actually we get something much stronger than only having a decomposition, but we know that this decomposition is stable under the Fourier operator. So for example, if you consider HD, A and so you can secretly think of this J as the perverse grading. So the HD and the second grading is I, then dual. Then if you apply F to this piece, so by this vanishing, this is nothing fancy here. You just write down the definition, and you realize that only 1 degree will contribute to this piece, and the image will be landing in B plus 2G minus 2I A, with the second gradient given by 2G minus I. And also for F inverse. So you decompose your cohomology into pieces, and this, you know that the Fourier transform operator on every piece, so the Fourier transform will respect this decomposition. And in particular, by looking at the degrees on both sides, you see that this only degree of this F which will contribute in the story is, so this degree is just the 2G minus I, and this degree will be just I. Okay, so then from this Fourier stability, we obtain immediately that I will just first write. This is how you think about this perverse equals Shen phenomenon in the abelian geometry. So if you apply Fk to any cohomology class on the dual side, this is recovering. So you use the Chen grading to recover the perverse grading, which is K here. So here you don't fix anything. You can feed in any class on the dual side, and you hit this. You apply this Fk, and on the other side you will recover exactly this case graded piece, which follows directly from this observation. So and also I would like to explain an interesting way for deduce the multiplicativity. In the stronger sense, which is that if you take a class in HD A with second grading given by I, and coupled with a class in HD prime, with the second grading given by I prime, it will go to HD plus D prime and A, and then I plus I prime. So, yes, I'm doing so. So there are several ways for deducing actually the stronger multiplicativity. So one of the easiest ways is that you prove that actually this HAJ is exactly given by a certain eigenspace with respect to some multiplication by n operator on the cohomology, and then obviously you know this multiplication by n operator is compatible with cut products. So this is the easiest approach. But I'm presenting a proof which uses a slightly different thing, because this is easier to, so this can be adapted to proving multiplicativity type results when there are singular fibers, where you don't have the group structure. So I give the proof of the multiplicativity using the Fourier transform and the convolution product. So this is actually it's an interesting argument which triggers our the general proof for the case with singular fibers. So the idea is that, okay, so we consider the multiplicativity on the A side, but it'll be easier to switch things to the A dual side. So the reason is that, you know, if on one side you consider the second grading I, which is a subtle grading in principle, but after going to the other side, the dual side, this second grading will be showing up in the cohomological grading, so that we can, so the cohomological grading is a much easier understood grading. So, okay, so let me just elaborate this idea. So if you start with alpha, which lies in HD and A, and the beta, which lies in HD prime. So this is I, and this is I prime. Okay, so I want to understand where alpha cup beta lies in. So obviously we know that it lies in HD plus D prime. But the second grading is not clear. But okay, so in order to decide that the second grading, we go to the dual side. So let's see how the dual side can help us. Well, so but going to the dual side, we know that. Okay, so in order to understand that the second grading on A, as I commented by looking at this formula, so it suffices to understand the cohomological gradient on the dual side, which is obvious. So we just need to understand F inverse alpha, the convolution product with F inverse beta. So we just need to understand what's the cohomological gradient of it. But we know we just know everything. So the F inverse of alpha would be like, looking at that formula, d plus 2g minus 2i. I can just ignore the second grading by only looking at, so this is F inverse beta, this lies in h d prime plus 2g minus 2i prime. And doing the convolution product, we see that the cohomological gradient would be just, you add these two and minus 2g. So this is d plus d prime plus 2g, one copy of 2g and minus 2 times I plus I prime. Okay, after having this, then you can read off this question mark immediately that it has to be I plus I prime. So this is an argument where you can use the cohomological gradient on the dual side to determine the second gradient on the original space. And this exactly this idea we will use to control the singular cases.
So, how to write this decomposition using only the Lefschetz decomposition? Because it's also you can recover it by the hard Lefschetz decomposition. No?
So you mean realizing this decomposition?
Yes, I think.
Yeah, I think this is good.
Just coefficients, because in any case you have the hard Lefschetz decomposition for the general abelian variety. It will provide irreducible Hodge structure, so you have no.
Yes. So yeah, it's true. So yeah, this decomposition actually there's no. You can realize this is a Lefschetz decomposition, yeah. But in this setting, it's essentially a similar story. So you have the E operator with the cut product with a relative ample, and the F operator, you can write this using the Fourier transform. It's a Fourier conjugate of this E operator. Yeah. And then the compact is the, yes. And this is a very good point, and I will come to that at the end. But so the general, so in the smooth case, there are three ways for thinking about this decomposition. The first is to use the group structure of A, which uses the multiplication by n map. The second is to use this F to produce projectors to cut into the cohomology into small pieces. And the third is to use a Lefschetz decomposition, which you have an SL2, but still at a certain point you use F. Okay, then we can ask how these ingredients are generalized to the singular when your fibration has singular fibers. So yeah, this is what I'm going to explain. So for the general compatible Jacobian fibration, as I stated here, so that basically these considerations will be generalized with some compromise. So instead of having a decomposition, we cannot have a decomposition. We only have, as I'll explain, we only study filtrations, and these operators respect these filtrations nicely. And but then you can ask, how do you think about this Lefschetz decomposition in the singular setting? So now this is some work in progress, and we feel that this has something to do with the Lagrangian condition. So in general, if you consider arbitrary compatible Jacobian fibration, you don't expect these operators to be extended. You don't expect these operators are extended over singular fibers. But when it's a Lagrangian fibration, then we expect this. I'll explain this. Yeah, thanks for the comments. Okay, so here, so we see that once you have this strong Fourier vanishing, we get a motivic we get a decomposition of the cohomology, and these both gradients are easily understood in some sense. But then, okay, so at the second remark, I give a remark, which is how to prove this. Or is let's see if okay. So the upshot is that, or the I don't know, this is called upshot. So the point is that, so in order to prove this vanishing, we still we cannot avoid completely the multiplication by n. However, when doing so, we see that actually there's some interesting ideas. So instead of proving this identity directly, we prove a weaker statement. So this is due to dimension reason. By taking a Chen character of the the relative diagonal. So for dimensional reason, we know that if I plus j is not equal to, if k is not equal to 2g, then instead of proving every individual term to vanish, we know that the sum of them is vanished, is 0. This is due to dimensional reason. It's not that hard. And then okay, so this is I plus j is equal to k. But instead of this total sum, you want to separate every individual term. So the idea is that, okay, we can, so this happens on the relative product, so you can apply the operator, which is multiplication by n, on the first factor, and you pull back the right-hand side. Well, you know, this is 0, so after whatever operation you do on it, you get 0. On the other hand, this multiplication by n, actually, you see that it will scale one of the gradings. So for example, this is, so n, j, f, j inverse, fi. So it will scale one of the gradings, but you know this works for every n. So this forces you to have the zeros for every individual term. And this is really an interesting idea. Instead of proving the vanishing direct, a certain tautological relation directly, we'll prove a much weaker one and see how many operations we can do with these relations, and then we get more. And of course, in the singular setting, we don't have this, but there is an idea from K-theory which can help us to achieve and proving something like that, but not exactly that. So, okay, sorry. And this proves that the vanishing of the individual term.
If the fibration is weakly abelian, can you mimic a bit this action?
Well, you have this multiplication by n, and then over the smooth locus, then you can take its closure. Then this is no longer, yeah, so then, so for example, you won't have things like if you have alpha cut beta. So for Poback, you have the compatibility with, for example, the cut product. And then if you take the closure, then this is a correspondence, but it's very hard to control it, for example, with respect to the cut product or other things. But here the good thing is that we will make everything rely minimally on the multiplication by n. So we'll make everything rely more on this Fourier transform because, you know, in order to get Chen classes, you will consider this anyway. And this, yeah, so this is the informal remark is that this multiplication by n is you have three things: multiplication by n, Lefschetz decomposition, and the Fourier transform, and this is the hardest thing to be extended to singular fibers in some sense. Okay, now I'm switching to the singular case. So almost every step will go wrong in a smooth setting. But I'll explain what we can do. So recall that in the smooth setting we have three steps, three ingredients essentially. The first is that we get a Fourier transform on the coherent category, which helps us to provide, which helps us to produce certain coherent sheaves. And then we take the characteristic cycle, the characteristic classes with respect to this cycle, and we get cohomological correspondences. And the third step is that we need to produce, in order for these cycles to work well, we have to prove certain tautological relations. Okay, so the May theorem, the proof of the May theorem. So, okay, everything, as I said, in a single smooth case, will go wrong in this singular setting, but so here I consider this F, which is J bar to B with the smooth total space. So, okay, I'll see what, so the three ingredients, the first one, basically replace Mukai's transform by Arinkin's transform. So, as Davesh mentioned, we have for a Mukai kernel on the relative product. And actually, this is a very complicated object. So in the smooth case, this is just a line bundle, which is Poincare line bundle. But in the singular case, it's a very complicated object. And so I can tell you what it is, but in some sense, this is not helpful. So in fact, so what really this is we have, so we first see to the largest locus for which we can produce a Poincare line bundle. So this is okay over J cross J bar over B. So if one of the factor only involves line bundle and the other, you can have torsion-free sheaves. And this will, so the Poincare line bundle will be extended to this open locus. And then, at the end of the day, this P, this E, will be nothing but just a J lower star L, as proved by Arenkin. But of course, just by looking at this formula, it does not guarantee. So you can easily write down this formula, but it does not tell anything about. So it's no guarantee that this formula would work well. For example, it induces the Fourier transform, induces the derived equivalence of JC bar. But then this is the hard work by Arenkin, which proves this. Using a lot of ideas, for example, the Hyman's isospectral Hilbert schemes.
In the non-reduced case, when the fibers are not reduced, it's known that this sheaf doesn't work, or we just don't know if the derived equivalence is a derived equivalence?
You mean, for example,
you could do the same, no?
Yeah, you construct the line bundle whenever you can, and you do the cohomology extension.
Exactly.
Yeah, I don't know. I don't have it. Do you know? You just brutally just do cohomology extension. Is there any?
I would wager a fair amount of money that it doesn't work, but I don't know. But anyway.
Yeah, it's not true. We expect it to. Yeah, really. So this really comes at the end. So in the proof, it does not use this description, but use there's some other description of E from this using the Hilbert scheme argument. Okay, so then the second part is, of course, we can descend everything from the derived category to correspondences. For example, again, I'm going to use the cohomological language to write everything. So you have F. So F inverse. But the one subtlety is, so now I'm going to use a color chalk. Hope this works. Okay, I'll use the color chalk to box all the difference between this singular case and the smooth case. For example, here we still have the cut product, which is exchanged with convolution product, but this convolution product is no longer of pure degree. So this convolution product, if you start with something HD, and you start with, if you consider something HD prime, and you will be landing in H greater or equal to D plus D prime minus 2G, which is, so this is the correction terms.
How do you define a convolution without like the multiplication or?
No, in this case, so convolution is a general. So this is convolution is formal. So it's as long as so it's descent from the. So in the derived category, you have a convolution which is written down just by this E, and yeah, exactly. You take the then you have a derived category convolution kernel, and you descend it to cohomology. You get this one, and then. The reason you cannot have a pure degree operator, but only have this inequality because you have no control of the convolution kernel, but you only know that it's supported on a subset of expected codimension. But this higher chain character can all contribute. So, but yeah, if you think carefully about the convolution, then it's actually a miracle that the original one is of pure degree, because you can imagine. So you have taken the cut product of two things. But instead, you first take the Fourier transform, which are mixed degree operators. So this F are mixed degree, but after then you do some operators here and coming back, you become a pure degree thing. So it's very surprising actually this convolution in the smooth case is pure degree. So a priori it's not. But here you cannot control, so the only thing you can control is this one, which is from the dimension reason, as dimension of the support of the convolution kernel, as I Okay, so this is the first place where we see correction comparing to the smooth case, and we will see more. So the idea is that we will see a lot of corrections when we try to generalize things from the smooth case to the singular case, and but at the end of the day, we need some good luck. We need to show that all these corrections are intuitively in one direction, so that we don't get the good properties for the decomposition, a splitting of the filtration, but if we only consider filtrations, they still behave well. Okay, so this is the convolution. Well, the third is A prime, B prime, and C prime, which is, so in all the story, the C prime would be the motivic decomposition, like it's a decomposition of the relative diagonal, but now we only get motivic filtration. So let me try to make this. So the replacement of the Fourier vanishing now would be, the stronger Fourier vanishing would be just the Fourier vanishing, which is that with this Fourier operator defined by Arinkin's sheaf, we in general do not have the strong Fourier vanishing as we expect, as in the smooth case. But we have these tautological relations in this range. So let me draw the diagram. So this is I, and this is J. So so this is the diagonal. So previously we have the strong Fourier vanishing is that you have vanishing here and vanishing here. But now Fourier vanishing only tells you that vanishing here and then here you don't have it. In general, it's wrong when there are single factors. So again, I use a green box to describe the corrections. So in particular, since we do not have the Fourier vanishing as we expected as in the smooth case, so if you take F 2G minus I inverse, as before, we do not get projectors, orthogonal projectors, but this can help us to get semi-orthogonal projectors. So we can define the filtration, the pk, to be so in that still you have the relative diagonals splitting, which is of the form Fi composed with F2G minus I inverse here, and then we only collect the contribution of the indexes up to k. So, and then, so this Fourier vanishing tells us that if we, instead of asking for a decomposition, we always ask for, if we ask for filtration, then we have it. So this pk induces a filtration. So for example, we can check that if you have pk, which is the projecting to this, the case piece of the perverse filtration, and you compose it with k plus 1, and then you can expect this is nothing but just pk. Because, something like okay, so then to relate this to cohomology, then so that the perverse filtration, as a consequence of the Engel support theorem, we can show that the perverse filtration PK is just realized by this operator PK using the cycles from 0 to k. So this is just the image of PK, which view this as the operator on cohomology. And then, in order to handle the multiplicativity question, we still have to switch to the dual side. And then so then this is given by this argument. So if you take the F inverse of PK, and still we have that. So after going to the dual side, we can treat the perverse gradient by the cohomological gradient, which is easy to control. But now it's not a pure gradient anymore. So this is just half of it. So d plus 2g minus 2k.
So why did the operator induce really the perverse filtration? I mean, he induced one filtration. Why is the perverse?
Yeah, this is a consequence of the endow support theorem. You have to prove it. Yes. So you're surprised. For example, this is a relative cycle over B and X on the push-forward complex. And then in order to show this is a perverse filtration, you can reduce to you can imagine that you just need to show this is you show vanishing by taking certain perverse cohomology. And then since everything is on full support, you can you can reduce to the smooth fibers. And you use the fact that these projectors in the smooth C will split in the refiltration. So yeah, there's an argument here, which is not obvious, but in particular this relies on the Fourier transform theory over the smooth locus.
And you're using full support.
And we are using full support. Yes. Yeah, but the full support, the use of full support is not that essential. For example, if you have endoscopic loci, like in the SLN Qizheng case, you have to check. You basically, instead of just checking the most generic point, you have to check the generic point every support. But so yeah. Okay, so this is the third time we see a correction. When we trade cohomological perverse gradient with the cohomological gradient. But then, so this 1, 2, 3, and then they are, so we need to show that they are all in the sort of same direction, which instead of, which if you consider only a statement about filtrations, then it works. But, so the last 2 minutes, let me say briefly. So okay, so this is a Hyperkela trimester workshop. So we say a few things about the holomorphic symplectic setting and how this enters the picture. Okay, so so far, as I said, because of these green boxes, we don't expect to have we cannot prove a statement about the decomposition as in the Beauville decomposition case. We only have everything for the filtration. But really the question is whether it's that we cannot prove them, they are still true, or we even do not expect things like it are true for a decomposition. And so the question is whether there exists I'll call this generalized Beauville decomposition. And let me finish the talk by a little discussion on so really whether we can, so by this I mean a multiplicative. So basically you just write out all the conditions you have for the Beauville decomposition, but you replace the Leray filtration by the perverse filtration. A multiplicative splitting, a Fourier stable. Multiplicative splitting of the perverse filtration. Since we have this Arinking's Fourier transform operator, so this question makes sense for any compacted by Jacobian fibration as we with the total smooth space. Okay, so the answer for the conjecture is that no in general. So in general, there are some obstruction actually for you to have a multiplicative splitting of the perverse filtration. So the easiest, so for example, if you have a multiplicative splitting of the perverse filtration, there should be in a singular locus there should be some extension of the theta divisor which lies in that second piece of the filtration. Then you would expect to have such a relation and so this relation over the smooth locus, well, there's many interpretation of it, which might be relevant to, for example, the double ramification cycle relations. And then in order to, so we do not expect this to be true if you just extend it to the singular locus.
So you still work with irreducible things now? No, it's not clear.
Even for integral, perhaps we do not expect it. I think just even for stable, in the stable locus, this might not be true. But
it's not true.
It's true?
Not true.
It's not, okay. So, yeah, there's you can replace this by some DR cycle relation, but you have correction terms from the, let me just finish the discussion. So, but we expect to be, yes, so theorem, this last theorem. So yes, if this family of curve comes from a K3 surface. So more precisely, it is given by if the compacted by Jacobian is the Beauville-Mukai system associated with the K3 surface, then you can imagine in this case this relation is exactly fixed by the Beauville-Bogomolov-Fujiki form, and then you have then we can prove there is a splitting which is multiplicative and preserved by the Fourier transform operator.
But isn't there for this theta g plus 1, there is some formula over the...
You mean in singular locus?
In the singular locus. I don't exactly know now to generality. On the moduli space.
Yeah, so
maybe it doesn't cover all you want.
Yeah, so if you have like, so if you have, I don't know, some modular space of singular curve and you have this JC bar over it. Yeah, even...
No, but I think...
Johan probably can tell us how this relation looks like if you want to modify, but I don't think it's of this form.
No, yeah, I do.
You can, yeah, but if this is a Beauville-Mukai system associated with a K3 surface, then you can see this relation is fixed by, you can have such a relation by the Beauville-Bogomolov-Fujiki form, and then you can, so this obstruction is gone, and then but moreover you can show that you really can split the perverse filtration to make it for a stable, exactly like in the Beauville decomposition case. And also for a Hitching system, then there's some, like for example in the work of Mallet, Hausdorff, Mallet, Minetz, and Schiffman, they try to construct an SL, this SL2 triple, which should really just the decomposition of the cohomology, which is also in the Lagrangian case. So we expect even, no matter whether it's open or compact, then we at least expect this to be true in the Lagrangian setting. So, okay, I'm stopping here.